before we go back into repeated prisoners' dilemmas, I wanted to ask you guys for any feedback you could give me about how the webcasts have worked out, if they've been helpful to you. Anybody look at them? You guys are the ones that always come to class. You don't need to look at them. Tiffany.
They're all right. Sometimes if your internet connection's not very good, I don't know, there'll be a lot of buffering and you might not be able to watch the whole thing.
Okay.
Sometimes it's slow to download.
Okay, so but when the internet connection is working well, is it something that I should try and do in future years? That's one of the things I'm wondering about. Okay, I'm seeing nodding here, even among faces that I know I see most of the time in class. So that's a good thing. Are there things that the webcast does better or worse than posting the notes online or being here? I guess I was surprised. I've been surprised this quarter when people have come to my office just asking for help on homework, and like Tiffany, they've mentioned that they've been looking at the webcast, and I didn't necessarily think that the people who came to class would do that. I'm not saying it bad. Is it something you guys do to review? Or yeah.
It's good because you post your notes on, but watching you write the notes is different than just looking at the notes, because that way you can you're writing it with you.
Yes.
So if we already saw, like for me, I will come and then if I go back and watch the video of you doing it again, it's kind of like I'm in class again.
Okay. Kenyatta, right? Kenyatta is saying that for her, seeing somebody watching being able to see somebody do the process on the board is helpful. And I'm very glad you said that, because another thing that I've been thinking about, if I'm going to keep going with the webcast, would be switching to PowerPoint. And one of the main reasons why I don't do PowerPoint is, without me being able to know why, it just seems to me that you guys watching me write the way you're going to have to be writing, that there is something helpful about that. Okay, well, if you have other things occur to you about those webcasts, advantages, disadvantages, I do think that there is a hidden disadvantage, and I'll sort of tell you guys, even though you aren't the ones who are subject to it. I said at the beginning of the class that I wouldn't rely on the webcast, and I couldn't quite say why. And I've done some more thinking about that, and in particular, I talked about it with the TAs, and one of the TAs, Emily, I think put her finger on what my concern was. She said, I don't think I'd be able to concentrate. Okay, and I think that is an issue, that in a big class it can be hard to concentrate anyway, although you guys have been a good, lively group in that respect. But when you're by yourself, you're on the internet, and sometimes the connection is adding these distractions, I think it is harder to concentrate there. And so the one concern I have about the webcast is it makes it very easy to rely on that as sort of your main source of lecture, as opposed to the supplemental source that Kenyatta is describing. And that, I think, is not good, but I guess we'll see how that works out at the end. Okay. As I say, I'm interested in feedback on this. It's uncharted territory for me, so if you have other thoughts, email me, stop by, let your TA know. I'd be interested in that. Okay. So what we're going to do today is we're going to go over most of what we did on Tuesday again from a slightly higher perspective. Okay. Tuesday, I think most of us were sort of immersed in the nitty-gritty. We're comparing this infinite sum to that number, and I had a feeling that people were kind of losing track of the big picture there. And that's okay. The little picture had a lot going on in it, and I want you to be able to understand all those steps in the little picture. So I'm going to go over most of what we did on Tuesday at the beginning of class. This is a really good time to stop me if I go over anything too quickly, and then we'll sort of go on to a higher level of Zoom there. Okay, so the main question that we're interested in for this last section is when can we get cooperation in these situations where the individual incentives work against it, okay? When can the concern with having a reputation for being a good guy, being somebody who was willing to cooperate, when can that motivate people to overcome their immediate incentive to defect? It's a huge problem for human beings the world over in all kinds of cultures at all points in history. When can we get past the incentive to betray the people we interact with, and when can we cooperate with them? So that's sort of the big question. Going to a little lower level of Zoom right now, the way we're approaching that is we're looking at a repeated prisoner's dilemma. We're looking at a prisoner's dilemma that incorporates this possibility of rewards in the future balancing losses today. Okay, when can those rewards in the future overcome the short-term incentive to defect? And as we've done all quarter, when we set things up as any kind of a game, we're looking to see when some strategies are in equilibrium, when we're going to see some kinds of behavior, okay? When those kind of behavior patterns are self-reinforcing, when they lead neither player to have regrets, when they are best responses to each other. I just did my litany of terms that we always associate with Nash equilibrium. Okay? So right now we're looking at a potential Nash equilibrium in the repeated prisoner's dilemma. And we're asking, okay, well, when is it in equilibrium and when is it not in equilibrium? Okay, we've been doing that all along with single shot games. When do we see challengers fundraising in equilibrium? Well, in that very first game we started with, the answer was never, but then when we started making some of the payoffs more arbitrary, we found cases where it actually would. When do we see pure strategy equilibria in a game? When do we see mixed strategy equilibria in a game? Okay, those are the kind of questions we've been asking all along. Now we're just moving up and asking that in the repeated game context. And I'm making a big deal out of it because that's what all of Tuesday's lecture was about. Okay? When is it equilibrium for me to play Grim Trigger given that you are playing Grim Trigger? So it's exactly that Nash equilibrium idea. It's just now the payoffs are so much more complicated. That's one thing, because we have to think not only about our payoffs in this round, but our payoffs in future rounds of the game. The other thing that's complicated is because the game is being repeated over this infinite horizon, the set of other strategies, other things we could do besides Grim Trigger is so huge that we can't just go through a list and say, oh, it's better than this, it's better than that, it's better than the third thing, we're done. No, we have to find ways of organizing these other strategies. And that's what makes repeated prisoner's dilemmas, or repeated games in general, a harder topic. Okay? So that caveat aside, the answer here is, I meant to get a new blue pen last time and I didn't, so no blue today. The answer is the same answer we've had all along. Okay? The answer is when neither player can do better by playing a different strategy, given that the person they're playing with, their partner, plays Grim Trigger. Okay? So the inequalities that we were looking at the end of the class, what I'm going to begin to look at again very shortly, that led to a minimum discount factor, those were answering this specific question. Okay? Given that you're playing Grim Trigger, when am I happy that I played Grim Trigger? Okay? When I am happy that I played Grim Trigger, given that you're playing Grim Trigger, then Grim Trigger's in equilibrium, then we think we can have cooperation. When I'm unhappy that I played Grim Trigger, when I think, oh, should have cheated, it would have been better, then we're not in equilibrium. Then we can't be sustaining cooperation through Grim Trigger. One other point that I want to emphasize that I felt like I didn't emphasize enough on Tuesday is this word mutual. Okay? I am not alone in doing this when people are immersed in the world of repeated prisoner's dilemmas and we sort of know what we're looking for. It's very easy just to say, when is a Grim Trigger in equilibrium? Okay? I really want you guys always to remember, though, that it's both players playing Grim Trigger. It doesn't make sense to ask whether one player's strategy is in equilibrium without saying what the other person's strategy would be. You can't answer the question, is one strategy in equilibrium, without knowing the other player's strategy. Or at least you can't unless there's a dominant strategy there. Okay? But a Nash equilibrium always involves a strategy for both players. What we're doing now, and what I'm going to do for a little bit here, is we're focusing on a game where the two players are perfectly symmetric. Okay? They have the same actions, they have the same payoffs, so if we do the analysis for one player, we're done. We've done that with a lot of our simultaneous games. But what I'll do towards the middle of class will be a case where the two players aren't perfectly symmetric, where we will have to actually look at it differently from each player's point of view. Okay. All right. So now I'm just going to kind of recap what we did on Tuesday. We were working with the prisoner's dilemma that we've been working on for a while now. Strategies are slack off, work hard. It's player A here on the rows, player B on the columns. B can slack or work. Payoffs 0, 0, 3, 3. 5 when I slack off and you work hard, -2 when I work hard and you slack off. Okay. Okay. So that is, remember what that's called? What is that part of it? Just this one little thing that we do in each round? It's a stage game. Okay? Stage game is a prisoner's dilemma. That's what makes it a repeated prisoner's dilemma. The way I was approaching the repeated game was through these tables that would spell out the actions in each round of the stage game specified by mutual Grim Trigger, the payoffs associated with that for one player, and then I did a different version of that table with different strategies for player A, holding player B's strategies constant. Okay, so rather than just repeating that whole thing a couple of times, let me put it on the board. You'll have seen it before. There shouldn't be anything new. If I do something different than what I did on Tuesday, stop me because I probably made a mistake. Okay, so the first part of the table is A's, I'm going to say actions, and payoffs from Grim Trigger before, assuming B plays Grim Trigger. Okay. B is in green here because A is the person whose point of view I'm taking. B is going to be playing Grim Trigger in every version of the table. What A is doing is going to be different. Okay? So in this part of the table, when A is playing Grim Trigger, we're looking at A's action, B's action, A's payoff. Okay, and we're looking at it in round 1, round 2, round 3, round 4. It goes on and on forever, but we'll start to see a pattern. All right. When we're playing Grim Trigger, if you'll remember from Tuesday, says we cooperate unless somebody has defected in the past. If somebody has defected in the past, we defect. Nice and simple. Okay? If that's the strategy I'm playing, I'm player A in the first round, nobody's defected in the past. It's the first round. There is no past. Okay? So Grim Trigger says you start off nice. Player B is also playing Grim Trigger. B starts off nice. A gets a payoff of 3. Move to the next round. Now we do have a history. Okay? A says, look, we both cooperated last time. Grim Trigger says, as long as nobody's defected in the past, I'm supposed to cooperate. Okay, I'm going to cooperate again. B says that. And here we go. We just get all these cooperate, cooperates. This looks like a harmonious situation for these guys. And A is getting payoffs of 3 every time. Okay. So this was the first panel, and I guess I'll continue the way I was on Tuesday. I'm going to write the present value to A of Grim Trigger. Again, this is assuming that B plays Grim Trigger. We always, always, always have to make that assumption. The present value to A of Grim Trigger now is the 3 I'm going to get today, because we're cooperating, plus the 3 I'm going to get next time, multiplied by the discount factor. Okay, because next time's in the future. It's not worth as much to me as the present. It's not worth to me as much to me in part because I'm impatient, but it also incorporated into this delta is the possibility that we might not get to a future round. Okay, I might be struck by lightning. You might move to Australia. Okay, so delta is capturing not only just pure impatience, but also uncertainty. And as I said last week, it's actually very hard to disentangle those things. How much of impatience derives from uncertainty and how much is just plain old impatience. So we discount the payoff that we're going to get 1 period in the future by 1 discount factor. 2 periods in the future, we have to discount it twice. 3 periods in the future, we have to discount it 3 times. Okay, so we're getting here our pattern where I'm factoring out a 3 here. And I've got this infinite sum of delta, this number between 0 and 1, that I'm raising to successively higher and higher powers. Okay, so because delta is between 0 and 1, these higher and higher powers of it are getting smaller and smaller, as I showed on Tuesday, or I didn't show, as I asserted on Tuesday and encourage you to believe, this geometric sum converges precisely in the situation that we're in now. When delta is a number between 0 and 1, this infinite sum adds up to 1 over 1 minus delta. Okay, so that allows us to put a number on the present value of this indefinite stream of payments. Okay? Yes, Kiara.
Like, I'm not understanding, is the delta, when you have the delta to the 3rd power, like first, that's when you're in the place, when you're in the first column, you're sitting in the first one, you're looking at your future and like 3 times ahead of you, is that?
It's 3 times in the future.
And then, like, so if that's representing 3 times in the future, that's the rest of the column, so like, why does the second one come in that's 2 times in the future?
Let me see if I'm answering your question. This might not be it. One thing that is confusing with the exponents on the discount factors is if you think about them as how many periods in the future, then it exactly adds up. If you think about this as round 1, this is round 2, then you're always 1 off in the exponent. Okay? And the idea is that in the round that we're in, that's like round 0, we don't have to discount at all. Now, was that what you were asking, or were you asking something different? So close to? So just lining up here, what we have is in the payoff in the current round. Right now, I'm getting my payoff right now, no discounting. This is one round in future. If we were labeling it, though, we'd probably call this round 2. Okay? This is 2 rounds in the future, 3 rounds, okay? And then on and on and on there, okay? And the idea behind adding a factor of delta each time is that each chunk of time you have to wait, the idea is your benefits are losing the same amount of value every time. And so this is, people will call this conventional discounting. Last week, you'll remember, I told you that the evidence from psychology is that people are actually even more impatient than this. That is true. The math gets incredibly messy when that's the case. So we're going to stick with conventional discounting here. I should say that the math gets messy, but the basic results that we're going to find would still apply even with hyperbolic discounting, even with discount factor that is getting smaller over the periods at an even faster rate than this. Okay. So the important thing that we're doing in this step is we've got our indefinite sum here. Let me really emphasize that this is going off into infinity. These are all going off into infinity here. Even though we don't know exactly when our interactions are going to end, we can, because delta is incorporating our uncertainty about that, we could put a precise value on this stream of payoffs from future cooperation. Okay? So I'm really missing my blue this day. We've used the word shadow of the future. If you want to say, where's the shadow of the future? It's right here. Okay? All these terms after the one that we're in are the shadow of the future. Shadow of the future. Okay. All right, so this is my payoff from playing Grim Trigger. If you think about what is this the equivalent of in a single shot game, this is the equivalent of a payoff. Okay? So this work that we did here is getting us to the point where we're looking at one number in a single shot game. In a single shot game, we're always comparing one number to another number, and if it's a single shot game with more than 2 strategies, we're comparing that number to several other numbers. What we need to do is another table to get other present values to compare it to. In repeated games, we're not comparing a single payoff, we're comparing the stream of payoffs that we're going to get from all of our future interaction. Okay? So that's what we're going to do. That's what we're going to do right now. I think I'm going to erase this part, give myself a little more board here. Okay. All right. So another bit of terminology that I want to emphasize today that I think I was using on Tuesday without making a big deal of it is I want to draw your attention to 2 words that are related but not the same, and unfortunately they sound alike. Okay? It's the difference in this context between defect and deviate. Okay? If I could run time backwards, we'd use a different word for one of these, but just the way game theory developed, we use these 2 words, and they are different. So defect is an action in the single shot prisoner's dilemma. Okay, it's one thing you can do each time you play the game. Grim Trigger, the strategy in the repeated prisoner's dilemma, tells you to defect sometimes and cooperate others. Okay, so maybe that's another thing to put up. about it. That defect is the alternate to defect is cooperate. Okay? When we say deviate, we mean play a strategy different than grim trigger. Okay? So the strategy that we deviate to, the strategies that we're comparing, the potential deviations, will have some defects and some cooperates, or maybe it's just all defect, maybe it's just all cooperate. But deviate means play a strategy other than the potential equilibrium strategy. Okay, so this, in the context we're looking at right now, is a repeated game strategy different than grim trigger. Okay? So defect is a little action. Every time we play the prisoner's dilemma, we have to decide cooperate or defect. So our strategies in these repeated prisoner's dilemmas, which have to tell us what to do at any point in the game. Out here in round 5 tells me what to do if you've cooperated every other time. Tells me what to do if you've never cooperated, if you've always cooperated, okay? The strategies are big, complicated things in the repeated prisoner's dilemma. The actions are the little small units, defect or cooperate, okay? So you have to keep them straight. It's something where you have to watch me, especially towards the end of the lecture, because the words sound alike. If you think I say defect in a context where it should be deviate, please speak up. Okay? It's quite possible that I will do that, and the only silver lining would be if you caught me, everybody would learn from it. Okay? All right. Back on this word deviate. Our big question. When is mutual grim trigger in equilibrium? When neither player can do better by deviating. Okay, so this whole phrase here is what we mean when we say deviate. So what we started to do on Tuesday was to think of ways you could deviate from grim trigger. What are things we could do other than grim trigger? Okay, I think I was calling them alternate or something like that, but I'm going to now switch to the more conventional language, the language of Dixit and Skeeth, and I'm going to say here we're looking at A's, actions, and payoffs from deviation number 1, which is going to be defect always. Okay, we looked at this before. Again, because we're doing the Nash equilibrium analysis, we're going to leave B's strategy the same. Okay, so it's still B plays grim trigger. Okay, and I'm just going to keep the rows here, A's action, B's action, and A's payoff. Actually, no, I'm not going to do that because they're not going to line up. I use too much space here. So we'll just have A's action, B's action, A's payoff in round 1, round 2, round 3, round 4, and on and on and on. Okay, so now in this panel, what we're doing is we're thinking about one thing that A can do different from grim trigger. So this is the repeated game equivalent of what in a single shot game we do when we're comparing one payoff to another. Okay? We're looking for another number to compare to this. And we did this one before. One way that A could deviate from grim trigger, one strategy that might give A better payoffs than grim trigger, given that B is playing grim trigger, is just to be a bad guy, just defect. Okay? So my action is defect, defect, defect. B is playing Grim Trigger, so B starts off nice, the way Grim Trigger tells you to start off nice. And in that round, A's bad character, that's what it would look like, A's decision to be a bad guy is rewarded here, but B says, well, never again. Okay, Grim Trigger says, I'm never trusting you again. I'm going to defect against you for the rest of our lives. There is no hope for peace. I'm never going to get over this. Okay, and so from then on, A's payoffs are 0. Because for every subsequent round of the game, now B is playing this strategy as well. Okay, so B is playing the same strategy here, but the actual actions that we're seeing B take are different because B's strategy is a contingent strategy. Okay, remember that word was up on the board on Tuesday. Grim Trigger is a strategy that tells you what to do contingent on what your partner has done in past rounds of the game. So because A acted differently here, B is acting differently. Okay? That's why it's game theory. Okay? We want to calculate the present value to A, not of Grim Trigger here, but of this alternative, deviation number 1, and that was an easy one, okay? Because we set up this game so that it had 0 payoffs when both players defect. The present value of this deviation to A, okay, the present value of always defecting when your partner plays Grim Trigger is 5. Okay. This was a number that we could compare to 3 minus delta. Okay. And what we found, I'm not going to repeat all the analysis there, but we just looked to see when what I got from Grim Trigger was at least as good as what I'd get from deviating, and we found that deviation 1 is not worthwhile whenever delta is at least 2/5. Okay? If I am at least patient enough that the dollar I have to wait 1 round for is worth at least 40 cents to me, okay, then this deviant strategy does not look good to me. Okay? You don't have to be very patient to prefer Grim Trigger in this game. 40% discount factor is a pretty small level of patience. Okay? Okay. It's fine to write this and talk about this the other way. It's fine to also say that deviation 1 is worthwhile when the discount factor is less than 2/5. Okay? And then the conclusion then would be when the discount factor is less than 2/5, Grim Trigger can't be a Nash equilibrium. It can't be a Nash equilibrium because one player can do better by playing a different strategy, by deviating to a different strategy. Okay? This is a place where on your homeworks, on your problem sets, you absolutely have to write out some words surrounding your inequalities so that the reader and that you especially can remember whether you're looking at a condition that supports the equilibrium or a condition under which the equilibrium fails. People will write things both ways. Both are fine, but you just got to be clear. Yeah, Kyra. Why don't I repeat, and I'll even write the alternative way of saying this. Okay, so what I've got up here on the board is the deviation is not worthwhile when my discount factor is greater than or equal to 2/5. Okay, so when this is true, Grim Trigger is better than deviation number 1. And it's actually going to be true that when this is true, Grim Trigger is in equilibrium. But this is evidence in the direction of it being equilibrium. The other way I could write that same thing is I could say deviation number 1 is better than Grimm trigger, given that my partner is playing Grimm trigger. So it's just one person deviating whenever delta is less than 2/5. Okay? And the interpretation here actually would be clear. If the discount factor is less than 2/5, we've already shown that Grimm trigger can't be in equilibrium. Okay? Okay? Grimm trigger not a Nash equilibrium because player A prefers to deviate. Okay? You can get to either version of the inequality literally just by doing arbitrary algebra steps differently. So you do want to be prepared to think of it as a condition that supports equilibria or one that shows that the equilibrium is failing. Okay? The other thing to do when you're interpreting something like this is to step back and ask yourself whether it makes sense. Okay? Here, I'm saying when the discount factor is really small, Grimm trigger is not going to be in equilibrium. Okay, what I'm saying is when the discount factor is really small, it means that the value I place in the future is really small. That's what this discount factor is doing. It's telling me how much weight I give to those future benefits. If that's really small, these future benefits are not going to be enough to balance the fact that I'd rather have 5 right now. Okay? Over here, from the opposite point of view, I'm saying when my discount factor is sufficiently big, I don't want to deviate. Grimm trigger looks like my best choice, and it's because I'm giving, my discount factor is high, I'm giving a lot of weight to these future benefits. Yes, it would be nice to have 5 now, but I'm looking ahead. I'm thinking about all those future benefits, and I don't want to blow it by defecting now. Okay? So either way, touching base with the story of the problem can help you get your inequality going the right way. Your less than sign and your greater than sign. Okay. So why am I not done now? I've compared what I get from Grimm trigger to what I would get from deviating from Grimm trigger. What's left? Is this the only thing I could do differently? No, it's not. This is back to what I was saying earlier. This is the hassle with repeated games. There's lots of other things I could do. Okay? There's so many other patterns of cooperate and defect that I can't even begin to write them all down in tables like this. You know, I'd be going on for days and days and I'd never be done. What I have to do is I have to organize all of those other ways of deviating. Okay, this is what makes repeated games hard, but with Grimm trigger, because the strategy is so simple, we can actually, the simpler the strategy, the easier it is to organize the ways of deviating from it. So what I'm going to do now is I'm going to finish showing you the conditions under which Grimm trigger is a Nash equilibrium. I'm going to finish doing that by looking at 2 other deviations. One is close to the one that Elaine brought up at the end of class on Tuesday, and one is another one. Yes?
Given that the Nash equilibrium is no longer the Grimm trigger, would you still call that specific strategy?
So the question is, if we get to the point where this inequality isn't true, and so we know that Grimm trigger isn't in equilibrium, the question is, would we still call it a deviation strategy? Probably not. Calling a strategy a deviation is really something that makes sense in the context of looking at some other strategy. Okay? So once we found that Grimm trigger is not in equilibrium, then we have to start over again. What you don't want to do, and what I think is a tempting thing to do sometimes, is to think, okay, so here's a deviation from Grimm trigger that turns out to be a good idea. Does that mean it has to be part of an equilibrium? Sometimes yes, sometimes no. You have to start over again with whatever strategy you're thinking of as an equilibrium strategy in the kind of special place, and then deviations are defined relative to that. So that is like such a good point that I want to inspires me to use some color here. Okay, this, what it means to be a deviation is always in the context of question whether particular other strategy, not the world's greatest grammar here, see if I can do better when I'm done writing. Deviation is defined in the context of a question of whether a particular other strategy is Nash equilibrium or not. Okay, so the particular strategy we're focusing on here is Grimm trigger. If we found Grimm trigger wasn't in equilibrium, we might actually ask ourselves, well, are there other strategies that are in equilibrium? But then we would be back to the drawing board. We'd think of another strategy that would be a candidate, and then from that, define the deviations. Okay. All right. So 2 more strategies. And I'm going to call them deviation number 2 and 3. Deviation number 2 is one that we didn't talk about on Tuesday, but it's actually even a little bit simpler than the one that Elaine thought up. Okay, so this one says, deviation number 2 says, defect, then cooperate, then return to Grimm trigger. Okay. A's action, B's action, A's payoff. Okay, so this strategy is kind of a, oh, yeah, I defected just once. Just kidding. I'll be good from now on. Okay, and to show you I'll be good, I'll cooperate. That's the idea with Grimm trigger. Okay, so A is going to first defect, then cooperate. Okay, then go back to Grimm trigger. I'll leave you guys to think about that right now. B, though, we're doing the Nash equilibrium calculation. So B, of course, is still playing Grimm trigger. B is playing the same strategy in all of these parallel panels here. Okay, so B is going to start off cooperating. Okay. First round, A defects, B's had it. B is playing Grimm trigger. When B is playing Grimm trigger, none of this cooperating to apologize and make amends. No, that doesn't work with Grimm trigger. I'm B. I don't forgive anybody. I defect forever. Okay? So A's payoff here is going to be, yes, that first time I trusted you, you betrayed me, you got a payoff of 5, but now I'm going to defect against you forever, and I'm writing the wrong payoffs, aren't I? It's worse than this. Okay? You got 5 last time, A. Now, A, you think you're going to get on my good side by cooperating? Well, no, I'm sorry. I'm defecting, and you get your -2 for that. And you could go back to playing Grimm trigger, and we could get 0s throughout. You could keep trying to cooperate. See, if you go back to playing Grimm trigger, because now there have been defections in the past, if you're returning to Grimm trigger, you're going to do defection here. Another deviation that I'm not going to write here would be to have some amount of cooperating here. I'm really, really sorry. Look, I'm cooperating twice. I'm cooperating 3 times. If B is playing Grimm trigger, it doesn't matter. There's no amount of cooperation on A's part that will get B to start cooperating again. Okay? So the present value to A of deviation number 2 is, yes, I get 5 right now. Then I get negative 2 delta. And then, okay, then we've decided that we hate each other and we're going to get zeros from then on. Okay. Is this one ever going to be a better temptation? Is this going to be a more compelling potential deviation than the first one? No, right? Here, my present value is 5. I get my 5 now, I get zeros. Here, I get something less than 5. Okay, so this deviation is never going to be as compelling a deviation as Grimm trigger, as deviation number 1. Okay, anytime that this looks like a better thing to do than play Grimm trigger, this deviation is going to look even better. Okay, yes, Kenyatta. You can't defect at the end because you don't know when the end would be.
Oh, okay.
That's the key thing with this. That's why I keep emphasizing the indefiniteness of it. As soon as you can write down a last period, theoretically, even if it's, out here, period 1000 or something, that should be enough to unravel because it'll just bubble all the way back up. Okay, here we can just never be sure that we won't meet each other again. Okay? And let me even just step out for a minute and say, this fact about the prisoner's dilemma, about that need for some future, however tenuous, seems to be a necessary condition for overcoming these incentives to cheat, I think that's saying something really broad about human society. Okay? If we really, really know that we have no society, we're not a community, we're never going to see each other again, you're going off to your cave, I'm going off to mine, we're never going to this river again, then we're not going to cooperate. What makes a group a society, what makes a group able to overcome these prisoners' dilemmas is this idea that there might be some future together, that the people have some future together. Now there was another, okay, maybe not. Okay. All right, so this deviation didn't come up on Tuesday, and I think it probably didn't come up on Tuesday because many of you guys did this in your head, right? That with Grimm trigger, when one person is playing Grimm trigger, there's no point in trying to make restitution. I am making a point of it now because probably the last thing we'll do, or one of the last things we'll do next week, is to talk about another strategy that can support equilibrium cooperation in a repeated prisoner's dilemma is one that allows forgiveness. Okay, so I'm going to talk about that later. But Grimm trigger, what makes it Grimm is no forgiveness. There is no way to make up for defecting here. Okay. And what I'm going to do is I'm going to do a slightly, to return to the big narrative too, deviation number 2. This logic applies to any, use a capital letter, deviation that requires a player to cooperate after defecting. Okay. Remember how I said that there is just an infinite number of strategies here? This logic applies to a whole bunch of them. Okay. It applies to, I'm going to defect 3 times, and then I'm going to surprise them by cooperating. No, it's not going to work. Okay. The only time it's going to work, this is going to be better. Any strategy that asks you to cooperate after you've defected is going to be a worse strategy than the one that says just start off defecting. And the reason is the nature of Grimm trigger. That cooperating after there's been a defection doesn't give you any benefit. Okay? You've blown it in the past. You defected once, that's it. Okay. Then the third group of strategies is this group. I think maybe I'll just write it as a group here. Deviation number 3, deviation group 3 here would be to cooperate for a while and then defect. This idea of, lull them into thinking that you're good, okay, and then spring the defection on them. And on Tuesday, I thought about the example of, let's say you cooperate for 2 times and then you defect. Yeah, I'll do that one. I'll do that one again, and then I'll show you how the number of times you go before defecting doesn't really matter. Okay, so the big group here is defect after some number of rounds of cooperating. Okay, and we'll think right now of 2. Okay, so this weird alternate strategy is, it's not Grimm trigger. It says cooperate twice, then defect. So we have A's action, B's action, A's payoff, round 1, round 2, round 3, round 4, round 5. Okay, so I'm A. I'm doing the deviation here. I cooperate twice, and then I defect. And because up here we sort of learned that once you defect, it doesn't make sense to cooperate, I'm going to put defects in after here. We could think about this returning to Grimm trigger, or we could think about this just as unconditionally defecting. The actions will be the same, and the payoffs will be the same. B's action here, B is still playing Grimm trigger. We're still doing the Nash calculation here. So B starts off being nice. He cooperates. You cooperated. B says, okay, this is good. I'm still playing Grimm trigger. Nobody's defected. I'm cooperating again. And you cooperated again. And B gets to round 3 and says, well, here we are in round 3. Nobody's defected. Grimm trigger tells me I'm supposed to cooperate. I do. And bam, you spring the defect on him. Well, when he gets to round 4, he's done with you. And it's defect from then out. Okay. So here, we're getting the reward payoff in the first round. We both cooperated. We're getting it in the second round. Here in round 3, this is the juicy round for me, I get my 5 because you weren't expecting me to defect, and I did. And now I'm going to get 0 from then on, but maybe this is worthwhile. Okay, that was the idea we were entertaining. So the present value to A of this, deviation number 3, is 3 plus delta 3 plus 5. Okay. So then the question is this payoff? Delta squared, thank you. Thank you. Yeah, that's right. 5 is nice. It's way bigger than 3, but it's still 2 periods in the future. Okay, it's still, and that's going to be important, actually. Okay. So this payoff that I get 2 periods in the future is discounted twice. It's only worth delta squared 5 to me right now when I'm adopting my strategy. So what I need to do now is compare this present value. It's zeros from then after. That's why I don't have my delta cubed, delta 4 terms here. I need to compare this to this. Okay? And it's a big board day for me today, so I'm going to go over here. And again, let's touch base with what we're doing now and how it's the analog of looking for a Nash equilibrium in a single-shot game. In a single-shot game, if it's a game with many strategies, okay, when we're comparing numbers, if we think that this cell is potentially a Nash equilibrium, okay, we have to compare the payoff from A, we'll just number the strategy, A playing strategy 2 to any other payoff that A could get holding B's strategy constant. Okay, right? We only compare the row players' payoffs in a particular column when we're in a single shot game. That's what we're doing with these panels of the table here. This would be deviation number 1, deviation number 2, deviation number 3. It's just we have to go to the extra work in repeated games to come up with present values here, because we're not just looking at one payoff, we're looking at a discounted stream of payoffs. Okay, so with our when is deviation 3 better than Grim Trigger? Okay, assuming that your partner is playing Grim Trigger. Okay. Well, the answer is when the present value of deviation number 3 is higher than the present value of Grim Trigger. So looking all the way over there at the present value of deviation number 3, it's 3 plus delta 3 plus delta squared 5. What I want to know is when is that better than 3 plus delta 3 plus delta squared 3 plus delta cubed 3 plus delta to the 4th 3. Okay, I've got my Grim Trigger has this messy stuff here. Now you'll remember from Tuesday that I actually found this easier to evaluate without the geometric sum formula, and I warned you that that's going to happen sometimes. Sometimes it's easier just to write it out. Sometimes you compress it into the formula. You just have to try it both ways. Here, it's easier not to immediately collapse this into 3 over 1 minus delta because we can actually cancel some terms here. Okay? We can subtract off our 3 plus delta 3 on both sides, and then we're left with an inequality that has at least delta squared in every term, so we could factor out a delta squared 2, and I'm factoring out a delta squared here. We're left with 5 greater than 3, factoring out the delta squared. Factoring out the delta squared, I'm left here with 3 delta, right? I only can take out 2 factors of delta there. Taking out 2 factors of delta there, I'm left with 3 delta squared, delta cubed, etc. Is my implicit delta to the 5th power term here. This is exactly the same condition as deviation number 1. See? Is 5 greater than this? Okay? You don't have to believe me. You don't have to see this. You don't have to rely on seeing that this is exactly the same as before. You can go through the same logic that we did before. Now that I've cleaned this up nicely, now I am going to use my formula for the geometric sum. Okay? Now I could say, okay, so when is 5 greater than 3 over 1 minus delta? Well, it's multiplying through here when 5 minus 5 delta is greater than 3. Moving back over here, it's when 2 is greater than 5 delta. It's when 2/5 is greater than delta. It's exactly before what we had before. Okay, and this is the condition for the deviation to be better. So this is the condition that says Grim Trigger fails as a Nash equilibrium. Yes? Okay. The way the question is, when do we use greater than and when do we use greater than or equal to? The deal with Nash equilibrium is that ties are okay. if you're deviating to another strategy and it's giving you just as good of a payoff, that the first strategy can be in equilibrium. Okay? So in the example that we're in right here, if we're wondering when is Grimm trigger in equilibrium, if it gives you just as good a payoff as always defecting, the ties go to Grimm trigger. Okay, we'll say yes, Grimm trigger is in equilibrium. So here, because I'm looking at it in terms of when does the equilibrium fail, the deviation has to be strictly greater. If I just wrote the thing the other way and I said, when is Grimm trigger, when does this go to support the equilibrium, I would say, when is Grimm trigger at least as good as? Okay, so kind of going back to this spot on the board, the strategy you're focusing on, the one that you're keeping the same for one player throughout, the one that's the candidate for equilibrium, that has to be at least as good. Okay? So that payoff, that present value of payoffs to that have to be greater than or equal to the other ones. When you look at it from the other side of it, the converse is then when you get the strict inequality. Okay? Okay. So now we really are done. And let's take a deep breath and really see that we're done. Okay? Now we really have shown that, where can I write my punchline? Okay, I'm going to write my punchline over here. Punchline of all these boards is that when is this stage game one that will support Grimm trigger? When is Grimm trigger Nash equilibrium in this game? When delta is greater than or equal to, emphasizing the point just made, 2/5. Okay, Elaine.
So in that situation, wouldn't you say Grimm trigger is the least as good as, like, deviation number one, so you have the equal sign, not better than?
You know, that's right. That's right. Elaine's pointing out that I got the math right, the word's not so good here. Let's say here, Grimm trigger is at least as good as. Okay. Okay, now how do we know that from all of this that we're really done? Remember, I was building this up as such a hard thing to do. Okay? Well, what we've done is we've thought about all the different things that you can do besides Grimm trigger. Okay, so one thing you can do besides Grimm trigger is you can just defect, just unconditionally defect. Okay? And we said, okay, well, sometimes you'll want to do that, but sometimes not. And as long as your discount factor is at least 2/5, you're not going to do better by unconditionally defecting. Okay, so again, emphasizing this point, Grimm trigger is at least as good as, the other one is not better than. The one side has a weak inequality, the other has a strict inequality. So that was part of it. Another set of things you could do is you could cooperate after defecting. And we said, no, that's never going to get you anywhere. That's not a good strategy because you won't ever be forgiven. Okay? So that rules out a whole bunch of other ways of deviating from Grimm trigger. The final thing you can do, too many boards here, it's over here. Final thing you can do is you can defect after some cooperation. And again, it could be after 1, it could be after 7, it could be after any number here. And that's not going to be better except in the same cases when unconditional defection is better. Okay? So that's the overall equilibrium analysis. What you guys can do in your homework problems and on the test is enough for you guys to remember that the most tempting deviation in Grimm-Trigger is always defect. Okay? So for me, I'm the professor. It's my job to teach you the logic of it. If I want to show you guys that Grimm-Trigger is in equilibrium, I felt like I needed to go through all the different cases because you understand what a Nash equilibrium is and you understand that this isn't the only deviation. Okay? I had to do that. I'm not going to ask you to do that part on an exam. In particular, I'm not going to ask you to come up with some way of organizing the infinite number of strategies that any repeated game has. Okay? What I am going to ask you to do, what I'm asking you to do in this week's homework, is to apply what I've shown you here, which is this bottom line. Okay? Given any particular repeated prisoner's dilemma, the deviation you have to check is deviation number 1. Okay? So you can use this fact. Okay, so the last thing I'm going to do is I'm looking at your homework right now, and yeah, this is what I'm going to do. You guys have till Thursday for your next homework. Okay, you are in fine shape to do everything up through C, and it would be really, really good for you to start D, but the one thing, I think it was worthwhile doing this in the level of detail I did today, we didn't get to asymmetric payoffs. Okay? D has asymmetric payoffs. I strongly recommend you do everything up to D before Tuesday, but we're not going to collect those homeworks until Thursday. Okay? So, yeah.
Why is this more tempting than like deviating all the time in terms of problem?